Good morning to those who are here. Today is Wednesday, October 4th. For those who are not here, they are going to watch this one recorded later on. So I guess we're going to go today mainly, or we're going to talk mainly about the homework assignments that you guys have. I know a lot of you asked questions, and I know I answered a few in the beginning, but because there were so many questions, basically what I ended up doing is, because there were constraints at that time, especially leading to the midterm, that the focus really needed to be on the midterm because they have far more weight in this class than the actual homework or any other assignment for that matter. So the focus was actually on the midterms. Now that the midterms are over, the homework assignments have been extended at least to the 21st of October. I know some of them are still coming down the road. So the focus again is going to be on the homework assignments and how we tackle them. I'm going to address today 4 homework assignments. And we may do this again sometime early in November. At this point, it's not scheduled yet. So we may continue this one, so down the road. Again, you guys know also that we have other assignments, so let me start with those, because we have one that is that needs attention on a specific date, namely the lunar observation project, and that starts this Saturday. This Saturday is actual observation that you need to do for the moon. Of course, you need to scout for it. You need to start, the assignment starts actually day before, which is the Friday before Saturday, October 7th. And that day you're going to go in the evening, look for the moon. And if you don't see it, the idea is you come in the morning of Saturday and then you look for it. Let me give you a hint up start. It's going to be probably more likely in the morning, because today, when on the way here, around 6 a.m., the moon was actually right in the middle of the sky. It was really high in the sky. So the moon was visible this morning, actually, and most likely that's what's going to happen also Friday morning and also Saturday morning. So again, you might need to train yourself. The whole idea of doing it a day ahead is so that you train yourself so that you know exactly when to look for it. This morning also, if you happen to go out, don't lose the opportunity to see also Venus. Venus is actually very, very high in the sky. It's toward the eastern skies, southern eastern skies, and it's going to be bright. It's going to be the brightest star, the brightest object after the moon. So you're not going to miss it. So again, look at Venus. Mercury, you cannot see it unless you are in an open area. I mean, I couldn't see it this morning because of the mountains where we live, and also because of the city, because it was not too high in the horizon. It was just a little above the horizon, so you cannot really see Mercury. But you can definitely, you're not going to miss Venus if you go tomorrow morning around 6 a.m. or so. You're going to see a very, very bright star in the sky, and it's going to dominate the sky after the moon. So again, this is an assignment. And also, since we're not meeting next week, don't forget that we have also an observation next week. Of course, you're going to be reminded of it, but also the fact that that observation needs to be done. It's going to be on a Saturday. So I know the 14th is going to be the observation. And the day before, you can try to do it. You're not going to be able to see the moon on the 13th, the Friday before. But on the 14th, it's going to be actually a partial lunar eclipse in where we are right now. And you're encouraged to come to campus on that morning. It's going to be, starts around 9 a.m., slightly before that in terms of the solar eclipse. And we will be here in campus a lot earlier. And there will be a lot of activities, so you're encouraged to attend that event. If you cannot attend that event here on campus, you are still required to do that observation. It's part of your assignment anyway. So this is just to get stuff out of the way. Now the focus again is on the homework. So unless you guys have any questions, I'm going to start with homework number 1, the first assignment, which is due on the 21st, in about 2 weeks from today or so. Sounds good? or 3 weeks actually. Today is the 4th. Yeah, it's about slightly less than 3 weeks. Okay, so let me share. Thank you. Thank you, Melissa. So let me share with you the screen. And so this is homework number 1, okay? This is the first homework that we're gonna go through right now. So basically, the homeworks are straight off of the book. So if you have the online, option, go for it. Look for the units, look for the questions and start to answer them. If you don't know how to first answer these questions, you must really read the book, okay? The first question is, what is the phase of your moon during a solar eclipse? And that is going to happen on the 14th of October. Obviously, it's going to be a new moon. Okay. So that's the question, but you need to read. You need to read and you have to have the answer in full sentence. You cannot have the answer in just like short answers like that. Okay. Which brings me to the next question is, why don't we have lunar eclipses and solar eclipses on a regular basis every month? Because again, if the moon were to align itself with between the Earth and the sun for the solar eclipse, and the Earth aligns itself between the moon and the sun for the lunar eclipse. So why don't we see that every month? Because we have a full moon every month and we have a new moon every month. Well, the idea has to do with how the axis of rotation of the moon around the Earth is, and the axis of rotation of the Earth around the sun is. That they're not lined up. They're tilted a little bit, and the moon fluctuates in its motion around that one by about 5 degrees. Again, you need to read the units and understand what's going on to be able to answer this question. So these are easy enough, hopefully, with the reading. The reason why the moon has a reddish color during total lunar eclipses because of the atmosphere of the Earth. And again, it has to do with how the rays of the sun being basically diffracted when they when they hit the upper layers of the atmosphere. Again, you must read these questions. Now comes the part where we do calculations. Okay. It said, show that the ratio of the moon's diameter to the Earth diameter is the same as the moon's distance to that from the Earth to the sun to that from the Earth to the moon. Okay, basically what you got to do is the following. There is the moon's radius. Okay, it's 1,738 kilometers. Pay attention to the unit because it matters a lot. So if I want it in meters, I have to multiply by 1,000. So it's going to be 1,738,000 meters. The reason why I want to match the units is because in here, if I read this units in here for the radius of the sun, it's 6.96 times 10 to the power 8 meters. So this is in meters. This too must be in meters. Or since this is in kilometers, this I have to divide it by 1,000 to make it in kilometers. No matter what, I must bring the units to match. Okay, so that's the first step. Then I do the ratio. It says the diameter of the moon, if I'm really careful with it, the moon's diameter to the sun's diameter. The diameter is just twice the radius. So twice this number after it converted to meters, and twice this number, their ratio, meaning you take one over the other, making sure that this is in meters, okay? The ratio, it says, must be the same as that the distance from the Earth to the moon to that of the Earth to the sun. The Earth to the moon is 384.4 thousand. Don't forget you have multiplying by 10 to the power 3 in here. 384.4 thousand kilometers. Again, they gave us this thing in kilometers. So if I want it in meters, I have to multiply by another 1,000. So it's 384.4 million meters. Okay. Again, I need to know how far the sun is from the Earth. The sun is from the Earth. And it's here, it's the astronomical unit. It's 1.495978706. I really don't need to go to that detail. It's about 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. 1.5. times 10 to the power 11. And again, they give us this in meters and this in kilometers. So one of them has to go to the other. Either we convert this one to kilometers by dividing by 1,000, or we multiply this one by 1,000 to make it into meters. Don't forget, there is already 1,000 in here. So 1,000 times 1,000, that's a million. So again, all I have to do is take this ratio over that ratio, making sure I have properly converted, to this ratio over that ratio. Is this simple enough, or should I go a little bit more details for the few who are here? I need to know.
It's starting to make a little bit more sense, Professor. I'm still slightly confused, but you
Okay,
explaining
so
it is
let's let
definitely helping it out quite a bit, I
okay.
have to say.
Okay, so let me go back in here. Let me stop sharing the screen and let's get into a little bit more something where we can do handy stuff in here. Okay, where is that sharing thing in there? Sharing, share, OneNote. Okay, so I have my OneNote in here, and hopefully it's gonna write in here. So it says, oh, I need to turn on this thing again. It says the radius of the sun, let's start with that one first. It's 6.96 times, it's for practical purposes is 7, okay? 6.96 is 7. Times 10, if I read the number correctly, it's 10 to the power 8 meters. 696, what is it? Million meters, which is 696, no. 696 million. Yes, that's correct, because 10 to the power 8 is a million. But it is known to be about 700,000. It's much easier to remember this number, but in kilometers instead. So if you were to remember it, that's about 700,000 kilometers. The sun is about 1.4 million in diameter, which is twice this number. So if you want to keep it in meters, let's keep it in meters. But if we want to use the kilometers, that's fine. So this is the radius of the sun. The radius of the moon, on the other hand, is 1,738 kilometers. But again, I need to compare it to meters. So I have to multiply it by 1,000 to make it into meters. The ratio of these two numbers, one over the other, but making sure it's both of them are in meters, not this one. Okay? Ratio, whatever number you end up with, and that's the end of it. Okay, you compare that ratio to the distance from the Earth to the moon, from the Earth to the sun first, because we have to keep the sun on top now. So the distance from the Earth to the sun, that distance is 1.5 times 10 to the power, what is it, 11 meters? I mean, again, that's an astronomical unit in meters. This number is known to be 150 million kilometers. That's an easy way to remember it too, okay? The distance from the Earth to the sun. So one astronomical unit is 150. Divide that number by the distance from the Earth to the moon. The Earth to the moon, according to the table, it's telling me it's 384.4 thousand kilometers. And again, I have to multiply by another 1,000 to make it into a million. So it's 384.4 times 1,000. That is to make it in thousands, in kilometers. But then I have to multiply by another 1,000, and 1,000 times 1,000 is a million. Take this ratio again and compare the two ratios. You should find the same number, basically. And that's why you have solar eclipse, because the moon can come in here and cover the whole sun. Not half of it, not more than it is, just about it. I mean, I know this solar eclipse called an annular eclipse because it's not, the moon is actually a little bit further away. That's why it doesn't cover. So it's not exactly at 384. This is an average number. So when the moon is further away, it doesn't cover as much. If the moon is too close, then it's covered more than it needs. But if it's just the right distance, it covers just about enough. That's why we have solar eclipse. And that's also where we have lunar eclipse, okay? So in a sense, because of this ratio, okay? But that's really the whole idea of this exercise. Is this clear enough now? So just to take the two ratios and compare them, and you should find the ratio to be roughly about 400 on each side. Yes?
Yes, sir. Making sense. Thank you.
Okay, very good. So let's go back into, let's stop sharing this screen in here. Where is the sharing? On here. Okay, stop sharing. And let me go back in here and share where we were. Okay. So the next question is, no, this one also says a total solar eclipse over Africa on August 2nd, 2027. Actually, it's going to be part of Spain and North Africa. That's where the solar eclipse is going to happen on August 2nd of the year 2027. So it's not next year, in about what, 40 years from today, okay, roughly. Based on the Mayan method of predicting basically solar eclipses of 6,585 in the 8 hour, okay, between repetitions of similar eclipses, these are similar eclipses, when and where will the next solar eclipse happen? First of all, we need to answer the where. 8 hours would put us 8 hours would put us exactly here in because we are at in California, and basically the Pacific Standard Time is about 8 hours from the GMT, from what is it, the Universal Standard Time, Greenwich Time. Okay, and this solar eclipse that they're talking about in August 2nd of the year 2027 is going to happen in that zone, in the 0 hour. So if you add 8 hours to them, it's going to happen in the in here basically. Okay, so the next one is going to happen. We know what is going to happen based on this method. Add 8 hours to it. It's going to be in the Pacific Standard Time. It's going to be actually California and northern Mexico and all of this area in here. In Central America, that's where the solar eclipse is going to happen. That is the where. The when needs some thought. If I take the number, how many days are in the year? 365, correct? Yes? That's a fact, okay? So 365 days a year. And I have 6,585 days. If I divide 6,585 per 365, I would find 18 years and some change. Okay? So if I go back into, let me stop sharing this. And let me share, let me first of all fire a new version of this. I use as a calculator, I use GeoGebra. So if you're not familiar, use your any calculator, doesn't matter, even your hand, even your cell phone, if you like, okay? Whatever method that you like. Okay, so because it's kind of handy, I mean, I have it in here, so that's why I use it. So let me go back in sharing in here and share GeoGebra. So we said the cycle repeats, what is my, yeah. The cycle repeats every 6,585 days. So if I take that number and divide it by 365, that gives me 18 point something, okay? 18.04. At this point, we don't care about the difference. We know in 18 years from the year 2027. 18 years from the year 2027, 18 plus 27 is 45. So it's going to be in the year 2045. We need to know the month though, and we need to know the day. Okay, that's really that's what we need to do. So we need to know the day, when it's going to happen, and we know where it's going to happen based on that 8 hours. So what we do in this case is we have 6,585, deduct from it 18 years at the rate of 365. So that gives me 15 days difference. Remember, they said August 2nd of the year 2027 when it happened. And I need to add to it 15 days from August 2nd. That puts it August 17th, because the August 2nd plus 15 days, that's August 17th. August 17th of the year 2045. But that's not correct 100%. Let me tell you why. Because in the year 2028, that's a leap year. So that happens immediately after the year 2027. The next year is not 365. And I multiplied here by 365. That year is 366. So I have to remove 1 day because of that. So it's not August 17th, it's August 16th, actually. But that's not the only year leap year. We have actually the year 2032, the year 2036, the year 2040, and the year 2044. All of this 5 days, 5 years, they have an extra day. So I need to deduct another 5 days in here. Okay? From my calculations, because for each and every one of those years, there is an extra day. So what I did in this case, 6,585 days from August 2nd of the year 2027, there will be another eclipse. I counted how many years by multiplying 18 by 365, and I removed the leap years. There are 5 of them, 2028, 2032, 2036, 2040, and 2044. Those are the leap years between 2027 and 2045. Okay? So now we're left with 10 days after August 2nd. 10 days after August 2nd, we'll put it on August 12th of the year 2045. Okay? If you don't believe me, based that this calculation is not correct, all you have to do is Google it. But don't please put an answer. You really need to put the rationale for the whole answer. So if you go to, let me go into share with you the screen. You can Google it. What is my share? I just opened a browser, okay? Solar eclipse 2045. That's the year when we're going to. So it says in here August 12th, 2045. Okay? And it's going to give you even the path for it. So all you have to do is basically, but don't Google. I'm not going to accept the answer to Google. It's just to confirm. Okay? So you take 6,585, you divide that by 365 to find how many years. Now we know it's 18 years. 18 years from 2027, that's 2045. But then you need to know the month and the day. How do you know the month and the day? You deduct 18 years. Each year is 365. From 6,585, you will be left with 15. But that 15 includes some leap years. You need to remove them because not all of the years between 2027 and 2045 are regular years. There are some years that have more than 365. They're 366. And they turn out to be exactly 5 years, namely 2028, 2020, 2032, 2036, 2040, and 2044. Those are the leap years. Remove them from the calculation, and now you're back to August 12th of the year 2045, and you know the where based on the GMT, based on the universal, UTC, Universal Standard Time, compared to the Pacific Standard Time, which is exactly 8 hours. That puts it in our region. Make sense? Okay, very good. So you guys need to probably, for those who probably did not follow thoroughly, you really need to go through the calculations yourself and basically convince yourself that it's accurate. So let's stop. Let's go back into and share the homework assignments. So I think we finished this one. Let me go into the next homework assignment, which is homework number 2. Homework number 2 gives you basically 4 problems. Okay. And it gives you some numbers. It gives you, for example, the smallest. All of this homework are based on only one idea, all of them. And I will tell you what that is, okay? Let me read them all and we'll discuss them. Okay, with the exception of 11. I mean 10, 12, and 13, they have the same idea. It's the same repeating idea. So let's go. The smallest separation between Earth and Jupiter is 588 million kilometers, while the largest separation is 968 kilometers. You're asking, why is that so big a difference? Well, sometimes the Earth is just on the same side of Jupiter, so the distance 588 million. Of course, Jupiter is far away from the Earth and the moon, from the sun. I'm sorry, the sun. And the other time, 6 months from today, the Earth is going to be on the other side of the sun, and Jupiter hardly moves. It's very far, moves very slow. It takes 12 years to go once around the sun, whereas the Earth takes only 1 year to go around it. We're talking 6 months, even half of that. So Jupiter would have hardly moved. So at sometimes in the same year, Jupiter is very close, about 588, and the same year, it's going to be about 900 and something million kilometers. So that's basically the point in here, okay? Given that Jupiter has a physical diameter of 140,000 kilometers, Jupiter has about 70,000 kilometers in radius, so its diameter is twice as much, which is about 140,000 kilometers, which is huge compared to the Earth, which is only 6,000 kilometers in radius, which is about 12,000 in diameter. 12,000 versus 140,000 is a ridiculous number, okay? What are the largest and the smallest angular sizes? So that's question number 1. Question number 12, so we're going to go to it. It's similar. The cloud directly above you is about 10 degrees across. So now they gave us the degree. For Jupiter, they didn't give us the degree. They give us the physical size and the distance. And they want to know the degree. Here, they give us the degree. 10 degrees, this clouds. From the weather report, they're 2,200. So they give us the distance. Now they want to find the size. It's the same problem, except the first one, you know the size of Jupiter and the distance from the Jupiter, and they want to find the degree. Now, they gave us a degree for the cloud, and they give us a distance. So all we need now is the size of the cloud. That's one thing. Now, for the problem 13, the galaxy Andromeda, M31, is in many ways similar to our own galaxy, but slightly larger. The linear diameter of the Andromeda galaxy along its axis is about 140,000 light years. So now they gave us the size of Andromeda. It's about 140,000 light years, okay? Compared to our own galaxy, it's only 100,000. So this is actually slightly bigger than our own galaxy. But from our perspective, the Andromeda galaxy only has 3.8 degrees, 3.18 degrees. So now they give us a degree and the size. So they didn't give us the distance. And they want to know the distance. How far away is Andromeda? So all of these problems are variations of the same question. So let me go into my notes to explain the idea. Because all of them, it's the same formula basically, except they change variables. So let me go back and share. What is my OneNote? Okay. So let's talk about the idea in here. They are all based on the following. It's on. So you have an observer, you have a starting point. This is the distance or the radius or whatever you want to call it. For Andromeda, it's the distance. For Jupiter, it's the distance. For the cloud, is also the distance. So they gave us the cloud distance, 2,200 kilometers. No, not kilometers, meters, I'm sorry. Okay, about 2.2 kilometers. That's where the cloud are. They give us the angle, theta. I'm going to call it theta. And they want to know how big are the clouds. So this is the size of the cloud. That's that problem. For Andromeda, for Jupiter, they gave us how big Jupiter was. They gave us how far Jupiter is in 2 occasions, when Jupiter is close by and when Jupiter is far away. And they want to know the angular size of Jupiter when it's close or when it's far. For Andromeda galaxy, basically, they gave us the size of Andromeda galaxy. They give us the angle, and they want to know how far. So all of them are the same formula. Here's the formula. This ratio over the circumference is the same ratio as 360 degrees over the angle. That's it. So what you do in this case, 360 degrees over the angle. Angle has to be measured in degrees now. Okay, is the same ratio as the circumference. The circumference of a circle is 2 pi times the radius, or the 2 pi times the distance in this case, which is the radius, divided by the physical size. And this formula is actually in the book, okay? This formula is in the book. So that's basically it. So for the case of Jupiter, we know how big Jupiter is. I'm sorry, how far Jupiter is. That's 588 million on one occasion or 968 million on the other occasion. We know how big Jupiter is. It's 140,000 kilometers. Now we want to find theta. We're going to find two values because we're going to plug in two values for r. That's the answer to it. Okay. For the case of Andromeda, they gave us L, how big Andromeda is in light years. So you have to be careful in here. They say it's 140,000 light years. So the answer is going to be in light years for R, because they tell us how big the physical size is, 3.18 degrees. Okay, so you plug in this formula. Again, you're going to find how far it is. Okay, I put an R in here because that's a common name for radius, but in all of our problems in here, it's the distance. It's the distance. For the case of Jupiter, it's R is 966 million, or 968 million, I'm sorry, and or 588 million, depending if it's close or far. For Andromeda, we don't know the distance. We know how big Andromeda is, the physical size. We know also the angle, how big it is. Okay, for the cloud, we know how far it is. And we know how the angle is, 10 degrees. So they want to find how basically the physical size of the cloud, how much is it extended. Okay, so it's the same formula. You apply it 3 times for these problems. Sounds good, everybody? Or should we take one example to make sure that let's do Andromeda because it's fun. Okay, let's do Andromeda. Okay, thank you, Melissa, but let's do Andromeda anyway. Okay, so for Andromeda, we know L is 140,000 light years. So that's how far it is. Okay. We know theta. They give us theta. Let me quickly make sure that I don't give you the wrong numbers. Theta is 3.18 degrees. 3.18 degrees. So if I use this formula to find how far it is, it's going to be R. So it's going to be L, which is 140,000 times 360 divided by 318. And don't forget the 2 pi. And that should give me how far it is. So let me go in here into my, let me stop sharing this because I have a calculator handy. So let me share the same calculator I was using earlier. Where is she? Here. Okay. So I'm going to use the formula. So we have 360 times 140,000. The answer is going to be in light years because 140,000 light years. Okay. So how many zeros? Yeah. This is the answer is going to be, so I multiply 360 by 140,000 and I divide by 3.18 degrees. And also the product of 318 degrees and also 2 pi. So we need 2 pi. This calculator knows pi, so as the answer is going to be in light years and is going to be 2,522,455.7 light years. Basically 2.5 million. That's a good number. That's exactly how far Andromeda is. It's about 2.5 million light years. I mean, there is some change. 200,000 is not going to matter much. I mean, 20,000 is not going to matter. So it's 2.5 million light years from here, roughly. Make sense? So I just applied the formula. What I did in here is 360 divided by the angle, because they gave us the angle. And they gave us how big Andromeda is, the galaxy is, M31 is, which is 140,000 light years divided by 2 pi. And we found the answer to be about 2.5 million. So it's the same formula for all of these 3 problems. Now, let me stop sharing if I can find this. I'm using two screens and this thing jumps from one screen to the other. That's why I'm chasing it, okay? So let me go back in here and share with you the other assignment, which is slightly different than the other two. Can ever find it. What happened in here? Let's show more windows. Lost it. Let me bring it in focus because I lost the assignment, the page in here. Under my share things, I can't find it. Okay, so now let's stop this and let me go and share. Hopefully it's gonna pop up this first thing. Okay, here it is. So the other one in here, which is 11, is slightly different. Actually, it's similar to another question that you have in the lecture. It gives you, suppose you are an alien living on a fictitious war-like planet, and basically the point in here is the sun or the star is shining directly down a missile silo 1,000 miles to your south, while your location is the sun is 36 degrees. This is similar how Eratosthenes basically measured the size of the Earth. And it's in the lecture in there, which is 36 degrees. From straight overhead, what is the circumference of this planet and its radius? So once you find the circumference, all you have to do is divide it by 2 pi. So once you find the circumference. Okay, the ratio of the full circle, which is 360 degrees, over this angle of 36 degrees is 10. 360 divided by 36 is exactly 10. So the circumference is going to be 10 times this distance. So again, the way that we derived that formula actually was based on the ratio of the circumference over the arc, which was the size of the object. Is the same ratio of 360 degrees over the angle. As a matter of fact, it's the same formula too, except its application is slightly different now. It doesn't use directly that far. So 360 degrees over 36 degrees, that's 10. The ratio of the circumference, which we don't know, over 1,000 must be 10. So the circumference is 10 times 1,000, which is 10,000 kilometers. In order to find the radius, all you have to do is divide this number by 2 pi, and 2 pi is 6.28. So divide 10,000 by 6.28, it's going to be slightly over 1,000. So that's going to be the circumference of this planet, okay? Which would put it slightly less than the moon, actually, okay? So this homework hopefully is clear too. Sounds good? Yes?
Yes, thank you, Professor.
Okay, no problem. So let's move on. Homework 3. Homework 3 relies basically on the second law of Kepler, the third law of Kepler, I should say. P squared is equal to A cubed, where P is in years, the period of an object going around the sun, and A, which is the semi-major axis, is an astronomical unit, which is 150 million kilometers, okay? So it's going to be AU. So that's really the whole thing. So Ceres has an orbital period of 4.6. What is its semi-major axis? Once we find it, where in the solar system we're going to put it. So we really have to answer the first part first, namely, what is the semi-major axis? If the semi-major axis is more than 5, that means it's further than Jupiter. If it's less than 5, it's closer than Jupiter. Is it more than the semi-major axis of 1.5, which is that of Mars? If it turns out to be between 1.5 and 5, which is the correct answer, 5.2 for Jupiter and 1.52 for Mars, it's going to be between them. And it is between Mars and Jupiter, okay? And so we're going to explore the whole ideas first, okay? Said now, an object in the outer solar system has a semi-major axis of 526 astronomical units. It's 526 times further away from the sun than the Earth is from the sun. What is the orbital period? So we need to use the same law, actually, as the first one. How does this compare to Pluto's orbital period? So once you find its P, compare it, and in years, of course, to that of Pluto, which is 248. Pluto takes 248 years to go once around the sun. Okay. from the time it was discovered in the early of the 20th century until today, it did not even complete a full cycle around the sun. It did not even complete half a year, half a Pluto year. So that's the question. Suppose an asteroid is discovered. So now we're going to move on. So just to see basically the type of questions that we're dealing with for homework 3. For Michael, since you came in a little late, you need to watch the recording. We spent about 40 minutes on the first 2 questions. So make sure it's first 2 homework assignments. Make sure you go back to them, okay? Anyway, suppose an asteroid is discovered with an orbital period with an orbit that brings it as close as half an astronomical unit from the sun and as far as 5.5 astronomical units from the sun. What is the semi-major axis? Basically, its perihelion is 0.5, which is half an astronomical unit. Okay, half the distance between it and the Earth, between the Earth and the sun. Half that distance, so it brings it inside, but also it can be 5.5 times further away than Jupiter. Obviously, I have to add the 2 numbers. That's going to be the major axis, and divide them by 2. That gives me half the major axis, semi-major axis. So in this case, it's going to be 0.5 plus 5.5 is going to be 6, divided by 2, it's going to be 3. So its semi-major axis is 3. What is its orbital period? Again, we're going to be using the same law. So again, it's the same thing. At this point, we're going to use one of them, and it's going to answer all 3 of them. Let's explore number 4. If a comet orbits the sun, reaches 1 astronomical unit at its closest approach. That means it's as far as from the sun as the Earth is. And its orbital period is 27 years. So its P is 27 years. It takes 27 years to go once around the sun. What is its maximum distance from the sun? Now, the problem is different. It's still P squared is equal to A cubed. They gave us P, which is 27. We're going to square this number and root square it to find how far its semi-major axis. Once we find the semi-major axis, we double it to find the major axis and subtract 1 from it. Because 1 is as close as it's going to get from the sun. The difference is how far it's going to be from the sun. Again, it's the same law, except how the strategy, excuse me, I think I need to drink some water. I need to drink some water from last time. Yeah, this is from excuse me. So it's the same question, basically, we answered with the same strategy plan. So again, we're going to defer this one to add it to the others too, to the other 3. The last one, calculate the speed in kilometers per second of an asteroid in a circular orbit at 4 astronomical units by dividing the orbit circumference by its period. So we need the period. They didn't give us the period, but they gave us its circular orbit, which is in this case A. The radius of the circle is the semi-major axis. So in this case, A is equal to 4. So from here, we find P. Once we find P, we find the circumference and divide it by. So all of these 5 problems, they use the same law. So let me share with you the screen. And we're going to take 1 or 2 at random, and they should be the same thing. So let me share. As a matter of fact, yeah, let me stop sharing first. I'm sorry. Then just share. Stop sharing. And let me share. Let me actually move this to the next screen because it's kind of easier for me to keep it on that screen. Let me go back to Zoom and let me share. The OneNote. Okay. Bring the mouse over to this screen. I can find it. So here is for all of this set of problems, they use Kepler's third law. Third law of Kepler basically says P squared, the period squared, in years. This must be in years, not in seconds or anything like that, is equal to A cubed. A cubed is the distance, the semi-major axis. This is the semi-major axis. This is also in astronomical units for it, AUs. And AU is the distance from the Earth to the sun on average, okay, which is 150 million kilometers. We really don't need this number at this point. We may need it for the last problem. So all of these problems use that. So we have series. We have, I'm going to pick up two problems that I think are a little bit fun, honestly. But all of the others, they use that. For series, for example, they give you P, which is 4.6. Okay, years. You square this number by the calculator, and then you take its cubic root, and you compare that number. Okay, you compare that number and see it. You're going to find it between 1.52, that's Mars, and 5.2, that's Jupiter. So you're going to place it between Mars and Jupiter. If it's more than 5.2, I need to know about it. There must be an error somewhere in the calculation. If it's less than 1.52, that means it's between the Earth and Mars. Then I really need to know what went wrong, because it's a number between these two. I know series is between these two. Okay, so that's the first problem. The second problem for Sedna, it's 526 astronomical units. So if we use the same formula, they give us A, 526. We cube that number, which means that we multiply 526 times 526 times 526 3 times. And then we take its square root. Once we take its square root, it's going to give us its periodical period, how long it takes for Sedna to go once around the sun. It's going to be a big number, much bigger than that of Pluto. They gave you Pluto 248.1 years. So Sedna takes far longer to go around the sun than Pluto does. Take the ratio of the two. Compare the two, take the ratio of the two. That's the question, really. For question number 3, suppose an asteroid discovered has an astronomical closest approach of 0.5, and a furthest approach is 5.5. What is its semi-major axis? You add the two, as I said before, it's going to be 6, divided by 2, it's going to 3. It's going to be 3. So 3 is its A. So the A for that one is 3. When I cube that number, 3 times 3 times 3, 3 times is 27. Then I take its square root. Square root of 27 is slightly more than 5, because square root of 25 is 5, and square root of 36 is 6. So it's a number between 5 and 6. Okay, so it takes anywhere a number slightly more than 5 years to go once around the sun. Basically, that's the whole point of that. So that's answer 12. Now I'm going to do 13 and 14 because I think a little bit more involved. For 13, it gives you a comet, its closest approach. So we're going to do 13 together, okay? Okay, can I move it? No, I can't. Sorry. I have to use the mouse, and the mouse will be bad. Okay. So the perihelion is 1 astronomical unit. So let me explain what that is. Okay, so here is the sun, and the closest approach is 1 astronomical unit. In its furthest approach, we don't know. That's the question. But this whole thing, half of it is A, is the semi-major axis for that asteroid, and they tell us P is actually equal to 27. So we're going to square P, 27 squared, and then take its square root. So when I take 27 and square it, I'm going to go into my calculator in here since I have it open. So 27 squared, what is it? 27 squared, it's 729. So when I square this number, it's hard to control this mouse. So this is squared is 729. Now I'm going to take the cubic root of that. So I need a calculator. If you don't have a calculator, you're not going to be able to find that. So the cubic root of 729. The cubic root of 729, since I have that calculator open again. So 729, I know I'm not sharing the calculator, but hopefully you guys can do it if you have difficulty. The cubic root of 728 is exactly 9. So the answer is 9, okay? So that's 9 astronomical units. one of which is closest to the sun. That means the furthest distance is going to be 8 astronomical units. And that's the question there. What is the maximum distance? That's called the aphelion, actually, is going to be 8 astronomical units. The closest, I'm sorry. I made a mistake. Okay, I made a mistake. Sorry about that. Okay, let me fix it quickly. What we found was A. We need to double A first to find the major axis. This is the semi-major axis. This is the semi-major axis. That formula has. So I need to double it to find the major axis. So the major axis is equal to 2 times 9, which is 18. Now I deduct 1 from it. Now here is a picture. So there's sun. Here's the asteroid when it's its closest, 1 astronomical units, and its furthest approach is actually furthest from the sun is 17 astronomical units. So the picture I drew earlier is incorrect. Okay, hopefully you guys caught that one too. Okay, because the formula has the semi-major axis in it. So when we use this formula, we don't get the major axis, we get the semi-major axis. We have to double it to find the major axis. Okay, and that's basically then subtract 1 from it. When it's closest approach, the furthest approach is actually 17. That's one thing. Now calculate the speed. It says internet is unstable. Hopefully everything is fine. Okay, in kilometers per second of an asteroid. So they give us A, which is 4 astronomical, and by dividing its period. So we need to know what P is. Again, P. Why is the pen doesn't write anymore? I think this is an old pen now. Is equal to A cubed. So A cubed is 4 times 4 times 4, 4 times. I mean 3 times, I should say. 16 times 4 is 64. Okay. So that's basically 4 times 4 times 4 is 64. So the period is the square root of 64. And square root of 64 is 8 years. So this is going to take 8 years. Okay. That's simple math, actually. You don't really need a calculator for it. I mean, if you don't know it, just put it in a calculator. Square root of 64 is actually 8. 8 times 8 is 64. Anyway, so we have P. But then the speed is going to be the circumference, which is 2 pi times A. 2 pi times A, and A is 4. It's 2 pi times A divided by 8 years. So this is in AU per year. They don't want that. They want it in kilometers per second. AU is 150,000 kilometers. So all I have to do is multiply by 150,000 kilometers. A year is 365 days. A day is 24 hours. An hour is 3,600 seconds. Or 60 minutes times 60 seconds, which 3,600 seconds. And now all I have to do is multiply 2 times pi, which is 4. I mean times A, which is 4, divided by 8. Obviously, this is a big calculation, but hopefully you guys can carry it. 2 times pi, which is 6.28, times 4, which is 20-something, divided by 8, times 150,000, divided by 365, and 24, and 36 seconds, and the answer is going to be the speed in kilometers per second. It's going to be a big number, okay? Because this is an asteroid that is moving around super fast in here, okay? Makes sense, this problem too? All of these problems are requiring actually the third law of Kepler, P squared equals to A cubed, where P is in years and A is in astronomical units. Sounds good? We have about 6 more minutes. Thank you very much, Melissa. We have about 6 more minutes, so let's see if we can do something on the last homework assignment. Some of you don't have that assignment yet, okay? Anyway, this assignment is actually on unit Is it 41, I think, or something? What is the book? Here is the book. Yeah, it's from unit 41 on Venus. Okay. So okay, so let's discuss them in about 5 minutes, hopefully. And if it's not clear, please send me messages. And I think from the last problems I may have to send you an answer to it, okay? I may have to draw the diagram for you guys, namely, let me stop sharing first what I'm sharing right now and share with you these problems again. Share. Let me share again. And homework assignment. Okay. So for this one, 14, I think I'm going to send it to you guys, okay? I'm going to solve it quickly and post it on Canvas. So let's discuss this one. First of all, you have Venus's atmosphere has 4.6 times 10 to the power 20 kilograms of carbon dioxide. It's mainly carbon dioxide in its atmosphere. It's a lot of ridiculous amount of carbon dioxide. If all the atoms of oxygen in the carbon dioxide were combined, so somehow basically terraformed, so that we make them into water, H2O instead of carbon dioxide, what would be the total mass of water that we're going to make out of it? So somehow we're going to get some oxygen, hydrogen somewhere. I don't know from where because it doesn't have much. But we combine them to make water, okay? We have to probably bring an asteroid or something like that. But if we're going to bring an asteroid, why don't we bring one of the asteroids that is rich in water and be done with it? That could solve the problem. And that water will dissolve all of the carbon dioxide and the planet becomes terraformed. Anyway, so let's follow the problem, okay? So we have that much carbon dioxide in the atmosphere, and we're going to extract the oxygen off of it, combine it with hydrogen to make water. And they gave you some numbers in here. The mass, the atomic mass of hydrogen is 1, carbon is 12, oxygen is 16. That's all the elements you need in here. So what you do in this case? The atomic mass of carbon dioxide is going to be 12 for carbon, and twice oxygen, which is 16. So 2 times 16 is going to be 32, plus 12, that's 44. That's 44 grams per mole, okay? That is of carbon dioxide, basically, 44 grams per mole. But you don't have 1 mole. You have 4.6 times 10 to the power 20 kilograms. So what you could do in this case, you take 4.6 times 10 to the power 20 kilograms. And a kilogram, there's 1,000 grams. So you can convert it to grams to find how many moles, because the chemical formula always in grams per mole. So what you do in this case, 4.6 times 10 to the power 20 times 1,000, that makes it 10 to the power 23. And you divide that by 44. You're going to find how many moles of carbon dioxide you're going to get. Remove the carbon off of them, and that is how many twice oxygen you have. Basically, how many oxygen atoms you have. Whatever number you're going to have in there, because each mole will bring you 2 oxygen atoms. And one of those oxygen atoms is only needed to make water. So you're going to double that number. 4.6 times 10 to the power 23 divided by 44, and you double that number. You multiply by 2, you get how many oxygens you get. Obviously, the water weighs 2 grams for the oxygen, because each one of them is 1 gram. And the 16 grams for oxygen, that's 18 grams. 2 plus 16 is 18 grams per mole. So now you're going to divide that number by that many, or I'm sorry, you multiply that number by that many to find back on how much mass of oxygen you're going to get. I mean, of water you're going to get, because you get all of this now in water. Once you do that, you're going to find a number which is slightly less than this number for the case of Jupiter. For the case of Venus, you take the amount of oxygen, of water on the Earth, which is 1.4 times 10 to the power 21, divided by the number, and that gives you the ratio. You're going to find about 3 or 4 times more water on Earth than what you potentially could make on Venus. Okay. Now, from this question, from the mass of that you're going to find, how much mass? They tell you that 1,000 kilograms of water will fill 1 cubic meter. That's the density of water. So you divide that number that you find from here by 1,000 to find the volume of water. Okay. And at the end, you're going to assume basically that all of the water is somehow distributed on the surface of Venus. The surface of Venus of a sphere of radius 4 pi times r squared, where r, the radius of Venus, is slightly less than that of the Earth. The Earth radius is 6,400 kilometers. You can take 6,300 kilometers for Venus. Okay? You square that number and you make sure you convert it into meters, or into meters again, because this density in a cubic meter. So you multiply it by 1,000 again, and then you you square it and you multiply it by 4 pi, and you take the volume that you find from the previous and divide by that one, you find the height of the water. It's going to be less than a kilometer in height. Okay, it's going to be a thin, shallow ocean basically. Okay, so that's this problem. Do I need to, you guys, send you a little bit more notes on these problems? Because we ran out of time, really. We are 1 minute past the due time, and I have another class to go to. Do you think I should send more, probably hints on how to do this problem, probably to do them? Or that should be clear enough from this discussion? Because I'm going to send 14. 14 requires a little bit of thinking. Yes, no, maybe? What do you guys think for the few who are here?
Yes, please.
Okay, very good. So I think that's actually, I'm going to share with the rest of the class, because I think there is a little bit of thinking for these problems, not just 14. And hopefully you guys can should not have any difficulty with them. So I'm going to post them on Canvas, okay? Okay, I know we are 2 minutes past the due time, and at least the planned time. What is the stop sharing? It's always I lose track of this thing in here. And for those who are here, actually, it might be a good idea to go back and review these things too. And please watch for the homework number 4, basically the discussion a little bit more in detail of how to tackle even problem 1, that I think I gave it a little bit more time than the others. And especially 14, because that one requires a little bit more thinking. Basically, what it is that the rotation of Venus around its own axis is extremely slow compared to its revolution around the sun, compared to its rotation around the sun. So in this case, the question is, but that's not the only problem. The other problem is a backward motion. It's actually the sun rises in the east and sets in the west in that planet, because of the fact that it has backward rotation. And you're supposed to find that there is kind of a ratio of between the Earth and the when are you going to see which phase of that planet. That's the whole question for it. Okay. So thank you very much for coming into class. For those who are watching this recording recorded, and even for you guys, please don't miss those assignments on the lunar observations, and I will see you guys on Saturday the 14th. Thank you, and I will have this recording hopefully either tonight or early tomorrow morning. Thank you. Where is the stop recording?